All right. That's good.
Let me repeat your question. We have a question about turbulent and laminar flow. How do we know which one is turbulent? How do we know which one is laminar? For stratified flow, we can have top one laminar, bottom one laminar. We can also have top one to be turbulent and bottom one to be turbulent. We can have top as laminar flow and bottom as turbulent. And we can also have top as a turbulent and bottom as laminar, depending on Reynolds number of each phase. So it can be the combination, right, between laminar and turbulent. Okay. Elongated bubble flow. Most of the time, we will have kind of laminar flow for the liquid phase. If the liquid phase velocity is high enough, it may form a turbulent flow and it's cause a mixing and do this. Okay. Gas inside can be laminar. I think it should be laminar. Can it be turbulent? Have to calculate actually. For slug flow, this gas phase can be laminar flow, can be turbulent flow. Part of the liquid phase, this part in the slug body, most likely turbulent flow because it has the mixing. In the film region, most likely laminar flow, but it can also be turbulent flow. So turbulent flow and laminar flow happen in several parts of the flow itself. Okay. Annular flow, film can be laminar flow and can also be turbulent flow. Gas core, most of the time, almost always, turbulent flow. Okay. Annular wavy, a wavy annular, I think both kind of turbulent flow. We have to calculate Reynolds number of each phase. Or if we really want to know, we inject dye into it and see. So we inject ink into it and does it do this or it's like dispersed like that. Then we can tell whether it's laminar or turbulent. Otherwise, calculate the Reynolds number. Okay?
Sorry.
Yes.
For the stratified soup, you said you have turbulent and laminar, but don't you think you have wavy flow if you have any turbulence in any of them?
Oh. Maybe what I said is wrong. We will have to calculate to check, really check which one is turbulent or laminar. You may surprise that sometimes the calculation show you that just one phase is turbulent. Like top one is turbulent and bottom one is laminar and we have stratified smooth. For stratified smooth, can bottom phase be turbulent flow? Maybe. You think not? I haven't done the calculation. Maybe you tell me better. So you may have to do some calculation and tell me is it possible? Maybe it's not possible. Calculation is going to be next lecture, not this lecture yet. All right. Vertical flow. We have bubble flow. Bubble flow is not the same as dispersed bubble flow. Bubble flow look like that. Dispersed bubble flow look like that. The difference is dispersed bubble flow, there's no slip between phase. Gas and liquid travel at the same velocity as the superficial velocity. I mean, actual velocity is the same as superficial velocity. Oh, no, is that no? No, not the same, but
Actual velocity of both of them.
actual velocity of both phases are the same. There is no slip. Okay. For bubble flow, actual velocity of gas is faster than the actual velocity of liquid phase. There is a slip, but dispersed bubble flow doesn't have slip. Okay,
So gas is more here?
it's not about more or less. This is just a cartoon.
No, the velocity of gas
Oh, the velocity of gas
is higher.
is higher. Yes, I think so, because it has less density and by itself it tend to move up, right? And if we speed up liquid, this kind of help gas to flow faster. So yes, gas velocity is kind of higher. Slug flow, it looks like intermittent flow, bullet shape of gas bubble, come and go. Churn flow is like shaking a bottle of water, very chaotic, kind of. It is systematic, but it is a chaotic system. Churn flow happen mostly in the entrance part of slug flow. So when we have long vertical subsea riser, so this part we may see churn flow, and when it's fully developed, we will see slug flow. Okay. Let's take a look. How does it look like? Bubble flow. Gas bubble inside liquid phase, and bubble move around. It's not just move straight, right? It can like move sideways, right? And there's a slip between the phase. Actual velocity of bubble is faster than liquid. Slug flow. Wow, Taylor bubble. This is gas phase, right? This is at the end. Okay. And we will have, this is a Taylor bubble. So we have Taylor bubble zone. And this film is falling film. It can fall down, and at the end, it can have some kind of mixing. You should see this in the lab.
Do we have
It looks like that.
So is this one falling down? That's what you say?
This film on the side can fall down. Liquid over here move up. On average, liquid and gas go up, but some part of it, liquid, can fall down. Okay?
We don't have elongated bubble here, bubble flow.
Do we have elongated bubble flow?
Inverted.
They don't observe it and define it as flow pattern for vertical flow. They may lump it together. Let's take a look at churn flow. Okay, for churn flow, it's like shaking. Very chaotic, move up and down. Seem to be distorted slug or Taylor bubble. This is slow motion. I don't even know if it's flow up or flow down or something. Sometimes it have liquid in the middle, go up like that, and then it fall down. Don't want to take a look at it too long. Feel dizzy. Yes.
When it's falling down, is this an example of when the superficial velocity can be greater than?
Yes. Yes. Let's take a look at okay. This one will be better example, but okay. Let's take a look at annular vertical flow first. The answer is yes. If you take a look at it more. Annular flow, vertical flow. Liquid film coating the wall, and film can move up, sometimes move down. Okay, sometimes the film is thin, sometimes the film is thick. Jia Cheng, you awake? Okay. So that's annular flow. Let's take a look at intermittent flow. Intermittent flow is both slug and elongated bubble we call intermittent flow. Okay? Slug is a subset of intermittent flow. Elongated bubble is a subset of intermittent flow. Annular flow is a continuous flow, it's not intermittent flow. Okay? Stratified is not intermittent flow. Take a look at this. Film, thick film falling down. This is one video from YouTube. Slug body moving up. Film going down. Slug body moving up. Is this chaotic enough to be churn flow? I don't think so. I would define this as slug flow. Okay. Film falling down. So actual velocity sometimes at some moment it is zero. It's like up and about to fall down. So it's zero, right? So at some point in time, actual velocity can be even zero and it's negative. So at that particular moment, actual velocity is less than superficial velocity. On average, it's moving up, but some part of the flow and sometimes it moves down. It happened. And another thing that I would like to mention is liquid film is not the same thickness. Sometimes it's thin, okay, at the back. Sometimes it's thicker, like, oh, right now it's very thin. Very thin here, you see, very thin. Sometimes it's thick. So, why liquid film thickness matter? Who want to answer anything? Anders. So, liquid film in the slug flow, why should it matter?
On the atom,
Why do we want to know the thickness of the liquid film inside the pipe?
you can find the actual velocity.
Does it, okay, yeah. Does it impact the pressure drop?
Yeah.
Temperature, heat transfer? Why do we want to know heat transfer? Calculate fluid property, right? Heat and momentum transfer, they are coupled to each other. And we can also use this to other applications like flow assurance in subsea pipeline. The magnitude of flow assurance problem in subsea pipeline is multiple $1 million. If I have 5 days of production loss, depending on the production rate, that is the amount of money that I lost. Instead of sell the oil, I have to wait and fix it. So the magnitude of the problem is multi-million dollars, okay? Especially in a long subsea pipeline. Question on the flow pattern. Okay. Arya, what did you bring next Wednesday?
Safety class.
Okay, yes. Where did you get the safety class? Walmart. There are several Walmart. Bring the safety class, please. Okay. It's a lab regulation. Alright. Let's take a look at 2.5. I update this a little bit. So if you downloaded it a long time ago, please download it again. This tells you about the formula. Okay. Liquid hold up, yes. Question, yes, Becca.
I'm just curious about the flame. Like, how do you know if it's thick or thin? Like, do you have to do experiments or?
The annular flow film thickness or slug flow film thickness, how do we know whether it's thick or thin? One way of doing it, if it is slug flow, we can put high-speed camera on the side. Okay. This is a pipe, we put high-speed camera and we look from the side. Take a picture, 1 hour 4,000 seconds, and then we will know how thick it is. Turbulent for annular flow, we can put borescope inside. It's kind of camera that can bend and then take a look inside the pipe. Some people use a test section with several holes. Okay, with several holes at a certain length. So once annular flow move past this section, the film is gone and we have just gas core, like to extract the film out. So when we know mass of the film out, they do some calculation and they know what is the film thickness. Sometimes they use wire mesh measurement. Some experimental technique have a several wire detect the temperature. Okay, so there are several techniques to do it. Let's take a look at the calculation. Okay, for your homework. Okay, you have to submit homework by next Wednesday, 10:50. Okay? Liquid volume fraction is liquid hold up. Average liquid hold up in the pipe. How do we get it? We may, have stratified flow, close the valve, and open the valve somewhere else, trap the liquid inside. So once we trap it, we drain all this liquid out, measure the amount of liquid, then we know the liquid hold up. So close both valves at the end to trap liquid inside, then we can get liquid hold up, right? Measure liquid volume. So liquid volume total divided by total volume capacity of the pipe is liquid hold up. So if I have slug flow and my slug front is over here, I trap it, I get a certain liquid volume divided by volume of the pipe, then I get liquid hold up one time. I do it again. Sometimes this bubble is like over here and I trap part of the bubble inside, some part is not trapped. So second liquid hold up will not be the same as the first liquid hold up, right? It depends on I trap what part of the Taylor bubble. Do I trap front of the Taylor bubble, or I can trap the whole Taylor bubble, or sometimes just a little bit of Taylor bubble inside, or sometimes I have two Taylor bubbles inside. So if I do enough of measurement, I'll get some kind of distribution, right? And I would say, that part is kind of, liquid hold up. Or I can, if I have very small section to trap it, very small section. So every time I trap just slug body, not the Taylor bubble, not the gas part. So every time I trap just that part, then I know liquid hold up of that part, right? So measurement is kind of tricky. Liquid hold up in different part of the pipe is not the same. If it's different time, it may not be the same either, right? So we can think about liquid hold up as area occupied by liquid divided by total area. Okay, that is liquid hold up. Superficial velocity. Superficial velocity is volumetric flow rate divided by total cross-section area. So it is like volumetric flow rate, right? Just divided by cross-section area. The superficial velocity tells us how much is coming in from the inlet. It tells us how much is coming in. Okay. For a constant volumetric flow rate Q and density rho in a straight pipe, superficial velocity is the same everywhere. True, right? So if Q is constant, Q can be constant if there is no phase change, there is no density change, then the volumetric flow rate is the same everywhere. Assume that there is no compression of the phase. Pipe area is the same, so superficial velocity is the same everywhere. The actual velocity is likely to be different from the superficial velocity. Now, I would like you to look at this picture. Okay? I have QL equal to 4 cubic meter per second. That's the input flow rate. And think about it as a belt, conveyor belt like that, moving the stuff around like a belt. Okay? So if the belt moves at the speed of 4 meters per second, so I put this box in, wait 1 second, this 4 box will move over there. And then I put another 4 box in, right? So eventually, it will stay apart like that, 4 meters apart, right? If the belt moves at 4 meters per second. You agree? Raymond, you agree? Say again. Sweta, do you agree with this picture? Yes. Pay attention, please. Okay. So if the belt moves at the speed of 4 meters per second, and we put 4 balls per second, so the balls will stay apart at the distance of 4 meters. If we move the belt faster, what happens? The distance that separates them from each other is longer. So if I move at 6 meters per second, so the distance that separates them is 6 meters. Okay, have some idea? So this is the analogy that Mr. Bateman used earlier, and I think it's kind of meaningful, so we add here. So you can see that actual velocity will tell us kind of liquid or what. You see this picture? If the actual velocity moves very slow, the box will accumulate, right? If it moves fast, it kind of stay apart. So the phase that move fast will have like lower hold up or lower fraction. So if I have VL move at 4 and I increase the speed to be 6, you would expect liquid hold up to be less, provided that VSL stay constant. This has to be constant. Okay. Clear enough? Okay. Calculation part. Formula. Did you have a chance to open the book that you buy $75? Open it and read it, okay? It will say this. Superficial velocity is Q over AP. Mixture velocity is adding them together divided by AP. There's this mixture velocity. It's VSL plus VSG. Okay. Liquid hold up. This liquid hold up is the average over the time delta T and over the pipe cross-section area. So the physical meaning of this equation is, first we do area integration, right? RD theta is the area integration in the cylindrical coordinate. And then we divide it by total area, IR squared, to get the fraction of liquid hold up. Then we do time average from T0 plus delta T over 2, or minus delta T over 2 to plus delta T over 2, divided by total time. So we get liquid hold up at a certain instant in time, a certain T0. Okay? Gas mole fraction is 1 minus liquid hold up. No slip liquid hold up is QL divided by total Q, or VSL divided by total of VM or VSL plus VSG. Slope, Slip, okay, had to be slip. Sorry about that. Slip velocity is the velocity of phase that move faster, which is most of the time is gas. Vg minus VL, that is slip velocity. Okay. So if slip velocity equal to 0, this means actual gas velocity and actual liquid velocity are the same. Actual velocity, okay, is flow rate divided by actual cross-section area, or VSL over HL. These two are the same, right? If you put the definition of HL, HL is AL divided by AP, right? So substitute it. VL is VSL over HL. VT is VST over alpha, or 1 minus HL. You good? Understand? Total mass flow rate. W is WL plus WG. Okay. Slip velocity, we already covered that. For no slip condition, Vg equal to VL, right? Or we have VST divided by 1 minus HL equal to VSL divided by HL. So do the math and we get HL equal to lambda L. This is for no slip. For no slip, Vg equal to VL, this makes lambda L equal to HL. Just a math, right? So take a look at this. For gas velocity to be higher than liquid velocity, VST divided by 1 minus HL minus VSL divided by HL will be more than 0, right? Because slip velocity is more than 0. Good? So this case is where we have slip. Then do a little bit of math. We will see that HL is greater than lambda L. Does it make sense? HL is greater than lambda L. So liquid hole up will be more than no slip liquid hole up. Let's go back and take a look at the picture. Okay. So if VSL and QL is the same, there's kind of no slip, right? Actually, we cannot say that. Top part has to be different phase, gas and liquid, but the concept is kind of the same. When we move faster, gas move faster, right? So when gas move faster, gas will be left in the system less. Liquid moves slower, so liquid kind of accumulate inside the system. So HL is more than lambda L for the case where gas velocity is higher than liquid velocity. So it's just the math part, move this to that, change side, and then we get that. Opposite is for the case where liquid velocity is greater than gas velocity. For liquid velocity that is greater than gas velocity, lambda L, no slip hole up will be more than actual hole up. Okay. This is another way to show you. So at the input, it's kind of depending on lambda L. We have two pipes connect to the inlet, right? Two pipes connect to the inlet. So at the input, at the inlet, the liquid hole up may depend on the input. But eventually, if gas moves faster, gas will be left in the system less. Liquid moves slower, so it's kind of accumulate. So after a while, the thickness can increase. So if you think as the belt So the belt kind of moves slow. We have the same input, so it's kind of accurate. Like this, okay? Okay. Believe it or not, just this. You can do homework. Good? It will take you some time, not that long. Okay, let's talk about something else. Drift velocity, VD. In the textbook, it says phase velocity relative to a surface moving at the mixture velocity or center of volume. So, liquid drift velocity is VL minus VM. So VM is center of volume velocity. Gas drift velocity is Vg minus Vm. So it's kind of the relative velocity, the drift velocity. You may say kind of the surface velocity. So drift velocity. We will go back to the drift velocity when we talk more in slug flow. Drift flux, okay, flux of phase through the surface moving at the center of volume velocity. So that is a physical meaning, flux of a phase through the surface moving at the center volume velocity. Mathematically, it's like that. Do we use it? Not really. Do I want you to know? Yes. Okay, we already talked about this. Example 1. Concurrent upward flow of solid and liquid where VSL is 0.15, VSS is 0.05. VSS is superficial solid velocity. This time we have concurrent. Liquid and gas move up, okay, concurrently. For no slip, lambda equal to 0.15 divided by 0.15 minus plus 0.05 equal to 0.75. That's for no slip. From this formula, V slip equal to VL minus VS. Substitute into form of HL, we get this formula, right? VSL divided by whole up is the actual velocity. Do the math, we get that. Okay. This part, you check if I do it right, please. Will you? Who will check? Oh, no one. Vanguard, will you check?
I'll check.
Siri, you check? June? Okay. See, they will check. So, after do the math, we get 0.26 and 1.1. Which value do we select? Vanguard. Yes. Why do we select that? Because it should be between 0 and 1. Yes. So we have to answer, but another answer is not the real answer. It should be between 0 and 1. Sometimes both of them are between 0 and 1. Which one do we select? Okay. Let's take a look at the case where particle moving down. Oh, we ran out of time, but I'm fine with that. So you may want to review this yourself a little bit, because what? It is exactly the same as the homework. Okay? I won't talk much. I will talk it on Monday, but please try before we talk anything about this. And as I said, if you know until this slide, you can do homework. If you get stuck, first step is to check this slide. It's kind of a solution, okay? Alright, good. See you on Monday. Bye-bye.